2.9 talks about linearization, linear approximation, and differentials. Linearization is linear, pretty much finding a straight line. That's what linear is. Linearization is finding a straight line to represent a function. Suppose we have a function y equal f of x, and we would like to figure out an approximation around x equal a. So what we do, we use a tangent line. You'll notice if I sketch this tangent line will be a very good approximation of this function as long as I don't divert from a by that much. So if you see around a by a small margin, the blue line and the black curve are almost the same. The further I move, the bigger the error will become. So I know that if this is a tangent line, the slope of the tangent is the derivative evaluated at a. So if I take y minus y1 equal m into x minus x1. Well, y minus, what's y1? y1 is f of a. The slope of the tangent we said was f prime of a into x minus, and what's x1? It's a. If I move that to the right, I will get y to equal f of a plus f prime of a times x minus a, and you notice that's what they call linearization. It's nothing more than the equation of a straight line, nothing fancy. So I want to find the equation of a straight line, tangent line basically. We've been doing that all along. Use linearization at the point pi over 3. If I plug pi over 3 in there, sine of pi over 3 is 1/2. I'm sorry, cosine. So it's pretty much y minus y1 equal m into x minus x1. There it is. All what I need to do is find the slope of the tangent, and that's very easy to find. Now, no need to memorize the formula. Pretty much, it's what we just did. In the back of the book, they would write it and make it a bit fancy. And they would say y, which is L of x equal, move this over, and there it is. So for now, we're just practicing how to find it. I'm going to show you how to use it in a minute. How about here, the same deal? We have this curve. We want to find a linear approximation for this, a straight line approximation. If x equal 4, y will be 1/4. So again, y minus y1 equal m into x minus x1. That will do the trick. So if I take a derivative, that is x to the -1, bring the power down, subtract 1 from the power, that's -1 over x squared, evaluated at x equal 4, that's -1 over 16, and there it is. Y would equal -1 over 16 plus 1/4, and when you move that plus 1/4, so you could say L of x is actually -x over 16 plus 1/2. What's so special about this? I could figure out solution very quickly because it's a linear equation. Instead of me using this function, especially when we're looking around for, and we're going to get to that point in a minute. So given y equal f of x, two things I need to get out of this. if I picked an x, and I added a delta x, this is x f of x, this is x plus delta x, f of x plus delta x. So keep in mind how this works. That's delta x, which is the change in the x. It turns out those are the same. Now, if I draw a tangent line, if I use this straight line, well, let's get a few things out of the way. One, if I find dy, it's right there. In reality, the change of y is actually all of this. So, dy and delta y, this is exact. This is an approximation. We're going to approximate what that is. And the reason for that, it's a lot of work, especially if it's an irrational number. I'll point that out, and I'll show how close we are. So, if I want delta y, which is f of x plus delta x minus f of x, it's simply that distance, y2 minus y1. So I could say f of x plus delta x equals f of x plus delta y, or I would say f of x plus delta x roughly equals f of x plus, and instead of delta y, the whole purpose of this section is to approximate it by dy. Now, if y equal f of x, and I take a derivative, I could cross multiply, and that's how I find delta y. So, delta y, which I'm going to approximate for dy all throughout, it's going to look like that. And I'll start with an example. So keep in mind, dy dx is simply y2 minus y1 over x2 minus x1. We're going to say, we're going to use differentials to approximate that. I want to approximate, and I'm going to point out both of those. I want to approximate the square root of 27.8. Well, this is what I'll say. I'll say f of x obviously is the square root of x. I need a perfect square. 25 is a perfect square. And what does that make delta x? If I go from 25, that will make delta x 2.8. So you'll notice delta x and dx are the same. Delta y is not the same. Well, if I use this, if I say the square root of 25 plus 2.8 is going to equal f of x, f of 25 plus dy. Well, the square root of 25 plus 2.8 is going to equal, what's f of 25? That's 5. How do you find dy? That's the whole purpose. dy is the derivative of that. That's 1 over twice the square root of x dx. dy is 1 over twice. What's x? X is 25. Put a 25 in there, that's a 5. dx is 2.8. dy is, this is 1 over 10, that's 0.28. So we're saying the square root of 25 is roughly 5.28. Let's see how true is that. If I get my calculator out and I plug in the square root of 27.8, what do I get? square root of 27.8. I'll get 5.272. Not bad. For me to be able to figure out the square root of 27.8 without using a calculator. So in reality, that is my answer. But getting 5.2, so you could say 5.3 to one decimal place accuracy, that's pretty good. Just to get an idea of what that is. That's the idea of approximating or linearization. Well, how about here? The whole goal is to find this dy, and we're going to use it in place the actual change. Evaluate dy for the given value. So if they gave you everything, you just have to practice that. Well, dy dx is actually twice the cosine of 2x, and you cross mod dx, so the change of y will be twice the cosine of 2 pi over 3. Dx is 0.03. Dy would be twice 60 degrees, that is 1/2. In the second quadrant is negative, right? That's a 1. So dy is roughly negative 0.03. We could find exact, but they're not asking for that. And we're going to match those. Here we go. Evaluate delta y dy for the given value of x and delta x. Then sketch the graph showing the segments. Well, okay, let's talk about this. And I meant that to be a y. So, well, let's figure out dy. From 1 squared is 1, to 1.2 and 1.2 squared. Delta y is nothing more than y2 minus y1 over x2 minus x1. Delta y is, and if I get my calculator out, it's still there, parentheses 1.2 squared minus 1 divided by 0.2, or you can put the whole thing, whatever makes you happy. I'm getting that to be 2.2. That's the exact change in y. If I want to approximate, I would say dy equals f prime of x. Well, what's the derivative? F prime of x dx. So dy is 2x dx. Dy is x is 1 times 0.2. dy is, and if you multiply 2 times 0.2, we will get okay, I figured out something wasn't adding up, because that's really a 0.4, and the difference was massive. But then it hit me what I did wrong. We said delta y. We didn't say dy dx. We said delta y. y2 minus y1, right? So that is actually 1.44 minus 1. That is 0.4. Okay, much better. I was really worried that 2.2 to 0.4, that happened if maybe you have an exponential function. Now let me show you and demonstrate what this is really doing. Y equal x squared. Okay, Now, if I draw a tangent, so this is 1, this is 2, I'm going from 1, and I'm going to go, this is 0.5, so 1.2 is about right there. So, this is delta y. This is 0.44. As for the tangent line, the tangent line would take, so this is delta x, the tangent line would take that value, and you notice it's below, which means this is going to be less than that. And this part right here, I know it's kind of hard to see, that part right there is the error in the approximation. So that's really what it is. The whole deal is to approximate delta y by using dy. Here's another problem. Use linear approximation or differentials to approximate the given number. I'm going to use both. Linear approximation, I'm going to say, well, I'm going to use f of x equal 1 over x. I'm going to let x equal 4 and delta x equal negative 0.01. Do you see that? So the goal is try and figure out what 1 over 3.99 equal. Now for this, it's not that bad. But if it was irrational or a sine or, a radical, then that would be a lot of work. So this is what we're going to do. We want to approximate what this equal. We're going to say, first we're going to say 1 divided by 1 divided by 4 minus 0.01 is going to be f of 4 plus delta y, right? That's me using f of x plus delta x equal. So we're going to say 1 over 3.99 is going to equal f of 4 is 1/4 plus dy. So we're going to approximate. Let's find dy. dy is negative 1 over x squared dx. dy is negative 1 over 16 times negative 0.01. That's a positive. And dy would be, 1 over 1600. So we're going to say 1 over 3.99 is roughly 1/4 plus 1 over 1600. I could say the LCD is 1600. Multiply this by 400, so that's 401. Now I could get my calculator and see how this works. I could say, what is, either you do the 1/4 plus 1 divided by 1600, it doesn't really matter, 401 over 1600, and that is 0. So our approximation is 0.25 and let's see what the actual number equals. What's 1 divided by 3.99? So this is our approximation. The exact is actually and do you see that we got it accurate to how many decimals? Five decimal places. Now this is how we would use differentials. If you want to use linear approximation, the same deal. You say let f of x. So this is linear approximation. This is differentials. F of x equal 1 over x. We would say x equal 4 and delta x equal negative 0.01. Well, let's see how this plays. if x equal 4, y is 1/4. Y minus y1 equal m into x minus x1. That's the equation of the line. How do you find the slope of the tangent? You take a derivative. Pretty much the same work, right? So evaluate x equal 4, that's negative 1/16. Did I do the same problem already? That sounds so familiar. Oh my god, I did that already. Crap. Okay, well, that wasn't intended. Okay. I could have did 1/x² and x equal 2. Okay, no big deal, same deal. So this is negative 1/16. So I'm saying the linear approximation for this line is negative 1/16x plus 1/4 plus 1/2. We did that already. And now if I say, what is L of 3.99? That's negative 1/16 times 3.99 plus 1/2. And I know what the exact answer is already, so let me find what the calculator tells me about my linear approximation. It turns out, so if I take 3.99 divided by 16 and take so that turns out to be 0.24. That's a negative, right? So if I take 0.5 minus that answer, I'm getting that to be negative. I'm not sure. I'll do it again. If I take 0.5 minus 3.99 divided by 16, yeah, it would be 3.99 divided by 16 is, oh yeah, 0.5 minus that. Okay, so if I take 0.5 minus that answer, okay, there it is. So the deal is, how far are you from the point? You can't divert from the point by that much. If you're close enough, then that should approximate. If you divert, say you go to 7, then you should do it again close to a perfect number, maybe a 9, maybe, you know. And you notice here, it is accurate to also 3 decimal places. That's the idea of linearization versus differential equations. Either of those will do, unless the problem specifically asks you to do one.